Hmm. All right, it doesn't look like anyone's planning on showing up for this lecture, and that's okay. This is an asynchronous course, but I just was trying to give anybody that might want to attend ample time to log in. It's now 1 minute after time for the class to start, so I really should be pressing on. I'm going to keep everything open and try to let people in as they come in, but I want to start off by letting you know we are starting in with chapter 17 in this PHY 242 course. So PHY 242 is what we call University Physics 2, and it starts off with some thermodynamics, or more specifically, atomic theory of matter and kinetic theory and that sort of stuff, transitioning into thermodynamics and ultimately ending in the second law of thermodynamics, or at least a brief introduction to the second law of thermodynamics. And then we go into Maxwell's equations. Uh, Maxwell's equations being the more typical uh, uh, subject matter of the second semester of a 242 course, though often, like I said, they do include some thermodynamics or maybe some quantum mechanics and stuff like that. So let us go ahead and begin. As I said, we're using Giancoli's fifth edition. Please see the syllabus for that. Also, of course, I did post a video introducing everyone in my physics courses to the way my syllabus works. That's on my YouTube channel as well, so please check that out. But we're starting with chapter 17 of Giancoli's fifth edition of Physics for Scientists and Engineers with Modern Physics. You're supposed to have a copy of the e-text. If you have a hard copy, that's great too. But the main thing is we're going to be going from that. So let me share my screen for a second just to show you what chapter 17 is supposed to cover, and then we'll go into using my iPad to work problems and stuff of that sort. A lot of this chapter is about the explanation of the atomic theory of matter, so we're going to address that as well. But here we go. So this is chapter 17 of our physics textbook. It says temperature, thermal expansion, and the ideal gas law. In fact, it sort of is an intro to what I called the atomic theory of matter for obvious reasons. But what we cover here is obviously section 17.1, atomic theory of matter, section 17.2, temperature and thermometers, section 17.3, thermal equilibrium, and the zeroth law of thermodynamics. As a rule of thumb, by the way, guys, if you ever get something that's called a law, in a physics or science course or anything, you might want to go ahead and make that make the assumption that that particular law, theorem, whatever it is, should be committed to memory in a verbatim sort of way, so that you can mull and stew it on your own time, just because it's in your brain at all times. Just look it over, think it over all the time, so that you can sort of think of the ramifications of it. So whenever you see something like law stated in the title of something like Newton's second law of motion, or Newton's first law of motion, or the zeroth law of thermodynamics, or the first law of thermodynamics, or the second law of thermodynamics, you should immediately start thinking, okay, I should commit that to memory. I should memorize it, and that's just a good rule of thumb. Uh, Anyways, thermal equilibrium, the zeroth law of thermodynamics is section 17.3. Thermal expansion is section 17.4. That's where we basically are realizing that as temperature increases, generally physical objects tend to increase in size. And in fact, every dimension of them, in some sense, as you'll see by some of the examples, every dimension of them, in some sense, increases as you increase the temperature. There are some anomalous behaviors at certain points. For instance, water, as a liquid, actually has a maximum density of at 4 degrees Celsius. Uh, so that when you're actually getting lower and lower temperatures of water, the density actually is trying to go down in some sense because you have sort of, if you imagine the curve of the density as if it's going to have a maximum at 4 degrees Celsius, then you'd expect it to look like this, reach a maximum, and then go like that. So if we go to the right of 4 degrees Celsius, like 5 degrees Celsius, that would mean the density is lower. And if I go next again, that's lower still. So evidently, when I go from, let's say, 6 degrees Celsius to 5 degrees Celsius, the actual density should increase. So the density increases as you get it colder and colder and colder until it reaches that critical 4 degrees Celsius, at which point it reaches its maximum density. And then when you go to 3 degrees Celsius, it's actually a lower density again, and 2 degrees Celsius is lower still, and 1 degree Celsius is lower still, and so on and so forth. So there are elements and compounds that behave in weird ways like this, and it's very interesting and extremely helpful that water happens to be one of them. For instance, you can imagine, since the density of water is a maximum at 4 degrees Celsius, then if let's say the Great Lakes all completely freeze in some, you know, ice age, if you will, or even just a regular wintertime, a pond freezes over, what you can say is if it's really gotten as cold as it possibly can, then the very bottom of that pond will have a temperature of 4 degrees Celsius. Uh, Again, that's probably the one sig, or excuse me, just a one sig fig. I'm not exactly sure if it's 3.98 or 4.0 or 4.02 or whatever. So just call it 4 degrees Celsius should be the maximum. And therefore, if you've had an infinite amount of time to get as cold as you want, the very bottom is going to stay at 4 degrees Celsius, which means it's going to be still in the liquid state. And in that liquid state, that means life can continue to exist. So that's kind of a nice little happenstance that we have with water. Section 17.5 is thermal stresses. That has an asterisk by it. The asterisk implies that it's optional for the instructor to choose or not choose. I like it. It's a very interesting calculation. I highly recommend you learn how to do that, and especially if you're going into engineering, it's really cool. But I am not going to test you on that. I try to remove such questions from the banks that I use for homework and for practice tests and stuff like that. But I might not have been completely successful on it, so you might occasionally run into them. I do not have a problem with you trying to learn how to do it just for a homework, so do so. If you find out that you got a wrong answer, for instance, on a particular homework assignment because it had that, then let me know and I'll do my best to give you credit back on that. I'm not sure I can do that with the practice tests or well, with the practice test. So be advised. But yes, it's not going to be covered. It should not appear as a question on an actual face-to-face test or a final exam. If it does, in fact, appear any section of or any questions related to section 17.5, if those appear in an actual test, then automatically I'm going to have to give you credit for the question, whether it's right or wrong. So the next section, 17.6, is the gas law and absolute temperature. We're specifically talking about gas laws here. So these are the laws that originally were found and were cobbled together in some sense to make what we now call the ideal gas law. Stuff like Boyle's law and Dalton's law and stuff of that sort. And it talks about the absolute temperature, which in the SI universe, the absolute temperature is measured in Kelvin. Notice I did not say degrees Kelvin. Degree you might have thought about this before, but for instance, why does temperature have degrees, but so does angular measure, and so does other things? Well, like for instance, the angle of a in a triangle, for instance, why does that use degrees as well as temperature and stuff? So, in general, what I try to tell students to understand is that when you put a degree on something, that's an indicator that it's based on an arbitrary scale. So, arbitrary scales often have some degree associated with it. So, these Celsius, or what we used to call centigrade temperature, that Celsius is, or that temperature is read in degrees Celsius or degrees centigrade, and it is somewhat arbitrary. Specifically, the Celsius scale was built based on water, as was the Fahrenheit scale based on water, and that's why we read degrees Fahrenheit, degrees Celsius. The degrees Celsius or degrees centigrade, whatever you want to call it, is based on it in the sense that we define the boiling, or excuse me, the freezing point of water to be 0 degrees Celsius, the boiling point of water to be 100 degrees Celsius, and then therefore the distance between the boiling and freezing of water at atmospheric pressure is 100 degrees. In the Fahrenheit case, we defined the temperature of the freezing of water to be 32 degrees Fahrenheit and the boiling of water to be 212 degrees Fahrenheit, so that the difference between them is 180 Fahrenheit degrees. Notice how I read Fahrenheit degrees for the difference in temperature between boiling and freezing, and I might not have done it with centigrade slash Celsius, but the temperature difference between boiling and freezing of water at 1 atmosphere pressure is 100 Celsius degrees there as well. So that's a trick that we use just to keep our wits about us. It doesn't necessarily have any holding, but it is valuable. So whenever you do a subtraction of one temperature minus another to find the change in temperature, we normally indicate that with a Fahrenheit degree or a Celsius degree, depending on what the units were you were using. So we call it Celsius degree or Fahrenheit degree with degree after the F or after the C. Whereas a temperature is just read as, for instance, 32 degrees Fahrenheit is the temperature at which water freezes at 1 atmosphere pressure. Okay, so keep that in mind. We will, of course, in some sense, define the Rankine scale so you'll know. I do expect you to be able to convert back and forth between Celsius and Fahrenheit, and I will teach you the way that is pedagogically most helpful. In other words, we've done research in education and learned that there's certain ways to learn the conversions between Celsius and Fahrenheit that are extremely helpful to students, and then other ways that aren't. For instance, just writing down a formula and using it, or memorizing the formula and using it, is not that helpful. The way we're going to teach you is a way to better own the actual Celsius and Fahrenheit scale and the conversion between them. The same thing with the conversion between Celsius and Kelvin. That one should make some reasonable sense as to how you do that, and the same thing between Fahrenheit and Rankine. But our job in this class is to teach you how to convert back and forth between Celsius and Fahrenheit, and then how to take your Celsius and convert that to Kelvin as well, because in the ideal gas law, the temperature must be in Kelvin. Okay? That's the absolute temperature scale, in other words. So after 17.6, which was the gas laws and absolute temperature, we introduced the ideal gas law. And then after the ideal gas law, we go into problem solving with the ideal gas law in section 17.8, and the ideal gas law in terms of molecules and Avogadro's number, that's section 17.9. That is a section that we will cover as well. Section 17.10 is ideal gas temperature scale, a standard. That's an interesting topic. It's something you should read just for your own edification and knowledge. But again, that's an optional section, and I will do my best to not have any test questions on that material. Okay, so it's going to be ignored basically. All right. Again, the same rules like I said before. That is what Chapter 17 is about, and you can look at the various examples that are in Chapter 17. I want to remind everybody, as I did in the syllabus, that sort of the main thing that you have to do with your textbook in the physics course is you, as a bare minimum, should be able to read the examples in the sections that are relevant to the course. So in my class, for instance, in Chapter 17, that means contains all the sections except for 17.5 and 17.10. So any examples in all those sections that aren't 17.5 and 17.10, every one of those examples you should know how to do so well that I could ask you that question without necessarily knowing it's the actual example, and you should be able to solve it without having to look up anything. Okay, if you're not at that level of mastery on the actual individual examples in the text, you're really not in a very good place necessarily to solve the physics problems for the homework, and certainly not for the practice tests and the test. So keep that in mind. That's sort of the minimal gold standard. I really hope students are reading their textbook beyond just reading the examples, because that's where you learn a lot of stuff that a lot of people might call trivia, but in actuality, it's what makes you be able to function and make judgments and critical estimations and stuff of that sort. So please read it as much as you can, and learn how to read. When you're reading a science book, you have to read quite slowly, for instance, at least for a while, so that you can accurately and precisely interpret what you're reading, in a way that helps you do something with that reading and that knowledge after you're finished. Because it's very common for a student, for instance, to read a whole chapter of a textbook and it seems perfectly obvious to them. All the examples seem perfectly obvious to them, and they sit down and try to solve the very first physics problem in the homeworks, for instance, like number one at the end of the chapter, and they can't do a thing. Okay, that's because they haven't read it as thoroughly as you'd like them to. It's really not easy to read science textbooks in a trivial way, and then get some knowledge from it. But ideally, one of the standards of a college-educated person is supposed to be that they can read an actual document and use that to conclude how to fulfill a process. Okay, so that's one of the advantages people have and employers have in employing college graduates, is they have some belief that hopefully that particular employee could be given, for instance, a white paper on a particular subject, and then read that white paper and then implement that for their company. Okay. All right, so let's get started by talking about the atomic theory of matter. And I'm going to do this without sharing the screen. It's mostly by talking as normal. I would do want to mention to you guys, specifically because I see that one of my students has now logged in and is paying attention to class. That's great. So I want to warn everybody that I do post these videos on my YouTube channel. So if you're, in hiding or trying to stay away from being posted on the internet, stuff like that, you need to, one, change your username with Zoom such that if that name ever appears on the screen, it won't actually show up on my YouTube channel. So you can just, change it to or in my case, my name's, Billy Younger, for instance. So you might change it to B Younger or B Young or Billy Y or something like that. You can change your username to that. And then when you actually are in here, if you wanted to do attendance, for instance, you could chat me your whole name. And in general, it seems like the chat file does not go across to YouTube. So I haven't found a way to find it anyways. But if anybody knows how to, let me know, because I need to make sure I'm not doing that. But the main thing is, if you have any of those things that prevent you from safely and confidently being on my YouTube channel with your whole name, you need to let me know, and you need to do those things as well to keep yourself from being on there. So now that I've remembered that, let's go ahead and start talking about this atomic theory of matter. And the atomic theory of matter is kind of interesting. Specifically, I mean, it's interesting in that we have this wonderful little Richard Feynman quote, which I'm in the process of trying to locate rather quickly. By looking in our course modules. I think I put that in helpful documents and links. So I'm looking right now to see Feynman quote, Feynman quote, Feynman quote. Uh, nope, I do not see it there. Am I even looking in the right place? That was the right place. Feynman, Feynman. I just saw it. That's what gave me the idea of talking about it to you guys. Uh, I just noticed that it was in one of my courses uh, files, so I figured it'd be a good thing. Let me check the file real quick, see if I see it in here. It looks as though I do not see. Ah, there it is. So here's the Feynman quote. I'm going to read to it. It says, if in some cataclysm all of scientific knowledge were to be destroyed and only one sentence passed on to the next generations of creatures, what statement would contain the most information in the fewest words? I believe it is the atomic hypothesis or the atomic fact or whatever you wish to call it, that all things are made of atoms, little particles that move around in perpetual motion, attracting each other when they are a little distance apart, but repelling upon being squeezed into one another. In that one sentence, you will see there is an enormous amount of information about the world, and if just a little imagination and thinking are applied. So that's Richard P. Feynman from Atoms in Motion, from the Feynman Lectures on Physics. So I like reading that specifically because you can see how a Nobel Prize winning physicist, a person who contributed to the Manhattan Project, a person who won a Nobel Prize in physics, a person that made physics really quite popular in many ways with his autobiographical books. Surely You Must Be Joking, Mr. Feynman. What Do You Care What Others Think? And Classic Feynman. There's some of the books that he's written that are autobiographical and entertaining. So I highly recommend you reading them. But also, like I said, it tells us something that someone who thinks a great deal about science and has a great deal to say about science has told us that the atomic hypothesis is a valuable thing. So the atomic hypothesis, if I remember correctly, it was Democritus who first suggested this. Democritus would have been an ancient Greek in what we now call the BCE or before the Common Era. So that's when he would have lived. And his idea was this. He said, I can imagine taking stuff. Now, I'm going to try to put this in the words of modern science, given what we know. So we know, for instance, that we can extract iron from certain types of rocks and minerals. If you imagine for a second that you took such a rock and you extruded the metal out of it and got it where it was just basically iron, then you could take that and say, let's apply this particular piece of iron, the idea that Democritus had. So Democritus's idea was you take an object. We're going to say, let's not take a object because that's a little bit loose and it's going to end up with a result that's not exactly accurate or not exactly what Democritus was saying. So let's imagine taking a chunk of iron that we know of, iron being the chemical symbol Fe, a part of the periodic table. So instead of Democritus imagining taking a chunk of matter and just doing this, we're going to say Democritus is taking a chunk of iron and doing this. So if you took that chunk of iron and you cut it in half and you threw part of it to the side, and then you took the remaining half and cut that in half, threw part of it to the side, took the remaining half, cut that in half, and you continue doing that, Democritus hypothesized there would be two possible results. There is one result would be you could do that forever, and he basically said, well, that doesn't make any sense. He could not imagine being able to cut something in half repeatedly in such a way that it would go on forever. So he threw that out based on common sense, and that left him with the other result, which was that you could cut it down to some point, at which point you couldn't cut it in half anymore. Uh, and as best I can understand, I haven't yet learned ancient Greek, nor very much Greek. I know the alphabet's about it, and I've been in the process of trying to learn some ancient Greek. But it's my understanding that in Greek, the word tham would stand for something that is divisible or cuttable or something like that, and the prefix means not. So when you say an atom, you're meaning not divisible. So that seems consistent with Democritus's statement. So I believe it to be correct. If you find out I'm wrong, please let me know because I do tell my students this, but it's based on my reading and my understanding of ancient Greek. But the main thing is he saw Democritus did, saw that when you take a chunk of matter and you cut it in half repeatedly, you should ultimately get to a smallest part that is in fact indivisible. Now, in the case that we use, which was iron, we know that the smallest part of iron that exists is what we call the atom, and that is where the name atom came from. But I should tell you that in modern physics and modern science, we know that you can, in fact, split the atom. But the nature of it is that the atom, if you split it, if you take some part of the iron atom away, specifically not the electrons, but the proton or the neutron, uh, and not even really the neutron to be honest with you, but specifically the proton. If you take the proton away, it inherently will become something other than iron, period. Now, if you take an electron away, it will be an ionized neutron, or excuse me, an ionized atom, but it still would chemically behave like iron. Similarly, if you took a neutron away, it wouldn't change its sign and it would still chemically behave like iron, but it wouldn't completely behave like iron because it'd be a different isotope of iron. That's the modern language that we use, where when we say isotopes, you have multiple isotopes of a given element. All of them chemically behave just like the element is supposed to. But if you went a little further and did a little bit more digging and research, you could discover that there is some difference between one version of iron and another version of iron that we call isotopes. Specifically, obviously, individual atoms would be have a different mass. If it's, in one case it has 14 neutrons, in another case it has 15 neutrons, right? Obviously that would make a difference. So that's where we are in the modern world, is if you take a element like iron and you divide it in half, divide it in half, divide it in half, divide it in half, keep on doing that, you will come to what we call a atom. And that in some sense is indivisible, but it's only indivisible in the sense that if you remove or add an actual proton, then it becomes an entirely different element. Okay, it's not that it completely disappears or that it completely uh, just can't be penetrated at all. It certainly can. It's just a matter of it's going to become something else. Which brings us to the next idea. If we now take, two of those elements, let's say iron and oxygen, and you put them together, you can get iron oxide, which you all know of as rust. So if you took a chunk of iron oxide and you cut it in half, and then you just got rid of a half and then took the other half and cut it in half, got rid of a half, took the other half and cut it in half, and kept doing that, you would in fact come down to a final part that in some sense is indivisible again, but it's not indivisible like the iron was. In this case, you would run into a smallest part of a compound, which modern science has told us is in fact a molecule. So we would have a molecule which would be basically some number of atoms of one type added to at least, well, I should say at least one atom of one type added to another atom that may or may not actually be a different type. For instance, we know that hydrogen, oxygen, and nitrogen are what we call diatomic elements. So they're naturally occurring in our atmosphere in the form of H2 or N2 or O2, meaning they're so reactive that oxygen doesn't just float around as a single oxygen atom around in our atmosphere. It floats around as an oxygen atom bonded to another oxygen atom because that's a more comfortable state. The same thing with hydrogen, the same thing with nitrogen. Now, those are called diatomic hydrogen, diatomic nitrogen, diatomic oxygen. And in fact, that is still a molecule. It's not a molecule that gives you an element or a compound that's different than the element itself. Now, if you took two or more atoms of two or more different varieties and you had them bond together in the special ways that atoms do bond through, for instance, electric forces of attraction and other things, which you hopefully learned about in chemistry, then that makes a molecule as well, but that makes a molecule of a compound. So, for instance, iron combined with oxygen can make the compound called rust. Hydrogen combined with oxygen can make a uh, hydronium atom or a hydroxide atom. I can't remember which one it is. So I apologize for using those two words, but the OH is what I'm talking about. I think that's the hydroxide atom, or excuse me, the hydroxide molecule. Or you could have it in a ratio of H, being two hydrogens with one oxygen, in which case it's water, or you could be H2O2, which means two hydrogens and two oxygens, and that's called hydrogen peroxide. So all of those are compounds, and when you get to that smallest part, it is a molecule, but it's not completely impenetrable, no more than the nucleus is, or maybe a little bit more than the atom is, or the nucleus, as I said before, is the part that's hard to break of the atom. But it can be broken, and it can be broken with less energy than it takes to pull out a neutron or put in a neutron or pull out a proton or put in a neutron. So protons and neutrons are in the nucleus, and that nucleus takes a whole nother order of magnitude in energy to break up an atom. But in the case of molecules, you're just trying to break the bonds that hold the individual atoms together. And if you were successful in doing that, and it is quite straightforward to do so. In some cases, it just takes heating it up. But when you did that, what you would have then is multiple elements behaving entirely differently than the original compound did. So, for instance, water looks nothing like hydrogen. It looks nothing like oxygen. It behaves, even in the liquid state of oxygen, it doesn't even behave necessarily the same way as water does. So the properties are entirely different, but there is some smallest part. Now, there's also things just called mixtures, and mixtures are stuff like salads, or if you put a number of atoms together and not all the atoms bond with the other atoms, then yeah, you're going to get a mixture, and all it takes is some of them not to form molecules. So then you have some atoms floating around by themselves that are separate elements, along with some atoms that got together to form compounds, along with other atoms that got together to form compounds, and so on and so forth. So that's just a mixture, and there's really no smallest part of that. You keep cutting it in half, and like a salad, if you kept taking parts out, you might end up with the last thing being, for instance, a cherry tomato, or you might end up with the last thing being a crouton, which is obviously yet another mixture, and so on and so forth. Okay. So that's the hypothesis of the atom. And to be straightforward, Democritus said, "Well, does this make sense with everyday reality?" And in fact, he concluded it did, because he was under the impression that, for instance, the reason why you can walk through central Rome and smell the wonderful smell of bread baking was, he imagined that these atoms would be breaking off of the bread and then floating off, not unlike pollen would float through the air. Okay. It turns out he's absolutely right. That's exactly what they do, except they're normally not necessarily atoms. They're usually molecules, and they're quite big molecules, but they do waft through the air like, pollen grains or something like that. And that turns out to be exactly how we smell. So if you're at some distance away and you're smelling bread, that means someone baking bread, or using some mechanism like heating it up, for instance, that has made the atoms. Excuse me. Atoms are molecules of the that are going into making up the bread. Those have become separated from the bread itself, and bouncing around as individual molecules or atoms in the air has managed to make its way to your nose and actually entered your nose. Okay, so that's the origins of smell. It's literally the atoms of the things you're smelling, or the molecules of the things you're smelling, are entering your nose, and because of certain chemical processes that make up the biology of our sense of smell, we end up smelling the smell. You might not want to poke at that science too much, or you're going to find out some pretty disgusting things about the things you've smelled in your life. So I'll leave it at that, rather than the normal jokes I tell my face-to-face classes. Now, in addition to having that scenario that evidently there's some smallest part exists, and that smallest part can break off and enter your nose and give you a sense of smell, that kind of stuff. In addition to that, there's other things. Like Feynman said, that these atoms or molecules jiggle. They do. And in fact, what we learned as a modern scientist, we learned that they in fact vibrate in position and move around, and they just never sit still. The atoms and molecules never really truly can sit still. And in fact, if you were to, let's say, create a infinitely small or nearly infinitely small little gremlin creature that could go into the human body, let's say my human body, and it could stop time and stuff like that, we could send a gremlin into my body, and he would one by one take all the individual atoms or molecules that he could find in my body and say, "Hey, quickly, while I've got time stopped, how much do you weigh, Mr. Atom?" And he write down that number in grams. He said, "All right," our atomic mass unit says we're going to learn in a few minutes. Or how about you, Mr. Molecule? How much do you weigh? All right, you can write that down. All right, now that I got you here, in addition to how much do you weigh, what's your average velocity? You know, how fast are you going on average at any particular point in time? And he writes that number down and does the same thing for the molecules. And he does that over and over and over again until he has the mass and average velocity of every single molecule or atom in the human body that is called Mr. Younger. Okay, and I say body, I mean the whole thing, my head and everything. Now, if you took an average of that average kinetic energy, which we'll learn later is, or you actually already learned that because you've had the equivalent of 241, but basically kinetic energy is 1/2 times the mass of the body times the square of the velocity. So if you took 1/2 mv squared and calculated that for each of the atoms and molecules that that little gremlin work with, you would have a mess load of kinetic energies for each of the molecules and atoms. Now, if you averaged all those kinetic energies, in other words, you can imagine sort of taking each one and adding them together and then dividing it by the total number. The averaging process might be a little different for extreme accuracy here, but this would give you a good ballpark idea. But if you were to take an average of all those kinetic energies, it turns out you can pretty much multiply that average by a certain number, and out will spit your temperature in Kelvin. So that is now what we consider the modern definition of temperature. Is the modern definition of temperature in Kelvin is directly proportional to the average kinetic energy of the molecules or atoms making up the object whose temperature you're reporting. Okay, so that's a very big deal. The average molecule or atom kinetic energy that a given object has is directly related to, in other words, just a scalar multiple of, and that scalar multiple doesn't change from one atom to the next or from one body to the next, but it's just a scalar multiple, sort of not for everybody. It's just a scalar multiple of your temperature in Kelvin. So high temperature means high kinetic energy, low temperature means low kinetic energy. But the main thing is the kinetic energy on average of all the molecules or atoms that make up a substance is directly proportional to the temperature in Kelvin. Okay, so that's another modern thing that we have, furthering on the idea of the atomic theory of matter. Now, by thinking about that, thinking about the fact that as temperature goes up, the velocities or the kinetic energies of these atoms and molecules is increasing, then you might be able to reach some pretty neat conclusions. Like one of the conclusions you reach is, let's imagine, for instance, this little pencil, Apple Pencil. Let's imagine it being made of atoms or molecules. Now, at the very end of this, what indicates the very end of this pencil or the very point of this pencil is, in fact, a wall of atoms or molecules that make up the shape that we're seeing. But if we zoomed in on it, so like I keep reaching for my glasses that are no longer on my face. So, like if I grabbed and looked really close, I'd start to see a fuzzy line here, but it still looks pretty smooth. If I zoomed in again by a factor of 1,000, I might start to see that it's got some bumps and stuff like that as opposed to being perfectly smooth. But if I've zoomed in yet again, and assuming I actually could, you're going to keep zooming, zooming, zooming. What's eventually going to happen is you're going to look at an area that's literally smaller than the wavelength of visible light. And at that point, once you've reached an area where you're smaller than the visible wavelength, the wavelength of visible light, then your eyeballs, which see in the visible spectrum, can't really interact with the light like they're supposed to, and therefore you're not going to really technically see anything. But if you could make something equivalent to seeing even at that scale, what you would see is atoms and molecules moving all over the place really, really rapidly and going over huge distances relative in some sense to the atom itself. So, if it's a solid, for instance, it's not unreasonable to think that an atom might move as far from left to right as is the distance across the atom, or maybe even a multiple of the distance across the atom. So immediately with that, we think, okay, well, these things are moving, and that means the edge isn't quite well defined. So we have some idea that all measurements are going to be riddled with error, specifically because if we get more and more accurate, we're going to run into the area where the edge is actually moving, and it's not easy to define it. And even if we did define it, it's still an arbitrarily sort of made up estimation of what the edge is. So it's just packed with error. But not only that, if the temperature went up, that would make the jiggling more exaggerated, and that exaggerated jiggling would make the space that's comfortable between adjacent atoms or molecules, that would make that space have to be a little bigger, because otherwise you're going to have these atoms and molecules which never get so close that they stick together, but if they got in such a way that you increase the temperature, then the amplitude and the velocity of these atoms moving back and forth together gets larger and larger till they literally could possibly, in some sense, bump against each other. Then they're not going to be comfortable. Right. So you might expect the equilibrium position of adjacent atoms to get just a little further apart. If you can follow my train of thought on that, then what we've reached is an atomic theory of matter predicts the idea that matter actually expands when you heat it up and contracts when you cool it down. Obviously, we would run into certain issues depending on how molecules behave and interact with one another, or how atoms behave and interact with one another, such that certain things don't do that all the time. Like water, for instance, has a density that goes up, and reaches a maximum at 4 degrees Celsius and then goes down, 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 down. That's just an anomaly of water itself, specifically the molecules of water combined with another molecule of water can really fit in a nice lattice of atoms slash, in this case, molecules, uh, in such a perfect way that at 4 degrees Celsius they're closest together as they could possibly be. That's what's going on there. So now we've used the atomic theory of matter in some sense to argue that matter should expand upon increasing temperature and should contract upon decreasing temperature. So that's a pretty big deal. Another big deal is that we could predict, for instance, that since atoms and molecules exist, we don't expect half atoms and quarter atoms and eighths of an atom to exist. So we expect there to be a integer ratio regarding the mass of hydrogen. If you put hydrogen gas in a container and you put oxygen gas in a container, you know that it can make hydroxide ions, it can make water, it can make hydrogen peroxide, all those different things. But in each of those things, what you'll learn is that the mass of the hydrogen in a particular atom or molecule and the mass of the oxygen in a particular atom or molecule has a very distinct ratio that's related to integers. And that's exactly what we find. You can use that, in fact, to determine the chemical formula of an element or compound, or excuse me, of a compound. Once you have the mass ratios, because you know a particular hydrogen atom or a particular iron atom or a particular oxygen atom has a very specific weight. Once you account for the weights of the individual atoms, which obviously aren't integers, even in whatever units you use, you're not going to get such that all of them could be integers. One might be an integer, but or two or something, but not very many. So once you've taken into account the fact that oxygen atom has a different mass than a hydrogen atom, has a different mass than a nitrogen or an iron atom, so on and so forth, then you can divide that out in such a way that you get a nice numerical relationship between the number of hydrogen atoms and the number of oxygen atoms making up either water, hydroxide, or hydrogen peroxide, or the number of iron atoms and the number of oxygen atoms make a nice numerical ratio associated with iron oxide, which we call rust. So that's some of the principles that we get from talking about the atomic theory of matter. So now that we have that, I can go on and talk about the first thing that your book talks about, which is a new unit of mass, and it's called the unified atomic mass unit. So, and there's other names for it, but basically we just use the lowercase u for that. And I'm going to tell you it relates to the periodic table and in a very special way. So let me start off by go ahead and sharing my iPad screen with you all. So I'm going to turn on my iPad. Feel free to ask me questions, Matthew, if you have any. You can do so by typing in a chat to let me know that you have a question, or if your audio works, just speak up and say, "Mr. Younger, I don't understand something. Could you help me?" That's why I hold these at a special time so that you can interact with me, even though you don't have to. This is, like I said, an asynchronous class. So I'm clicking now on advanced, and I'm doing iPad, iPhone, AirPlay. Now I've got to share it on my iPad itself. So in a second, it should pop up a grid of graph paper. Yep, there it is. So you're now looking at my iPad screen, and you can see, of course, I have a link to my YouTube channel at the top. But what I'm saying here is there exists another unit of mass. So another unit of mass that is more convenient when dealing with atoms, molecules, protons, and neutrons. And that unit is given by the symbol lowercase u, which I will tell you is equal to about 1.6605 times 10 to the negative 27 kilograms. Now, you might think, oh crap, there's another factor or another number I have to commit to memory, but you really don't necessarily have to commit that to memory, especially if you're already familiar with Avogadro's number. So hopefully we all know what Avogadro's number is, but I will report to you, for instance, that Avogadro's number N sub A is about, and I should probably put this about symbol on that one too. This is about 6.022 times 10 to the 23rd. And I'll just say items per mole. Now, often books will just state this as as a unit of mole to the negative one power. That's fine too. I like to put the items up there to let you know that this is really Avogadro's number is really something related to moles, and it has to do with the number of items in a mole. So, if you've had chemistry in high school or anything before, you already know how to convert to moles. That's an important thing. We will need to do that. I will tell you right out now, just in case you haven't had chemistry before, it's not that big a deal. It's very straightforward to do. But the way you convert to moles is you take the atomic weight or the molecular weight of the substance that you have and divide it by the mass in the same units. or excuse me, divide the mass of it by the atomic weight or molecular weight, again, in the same units. And you might think, wait a second, I just see these numbers up here on the periodic table. I wish I had a periodic table in front of me. But I do know for a fact, for instance, that the molecular, or in this case, atomic weight of hydrogen is listed as 1.007. I think it's 7294 or something like that. So I'll write this in a different color just in case I'm wrong. It's something like that, okay? But it's normally just written on the periodic table without any units. Hopefully you have an idea what that unit is. Matthew, feel free to let me know if you think you do know what that unit is. It's always good to sort of chat that in if you wish. Gotcha. I just opened up my chat since I switched to this new form. I had to open it up again. Uh, do you recall exactly what units the mass is in the periodic table, Matthew? Really putting you on the spot. Literally, you're the only student here, and I'm going to badger you with asking you competence questions. Don't take that seriously. I'm just trying to interact with you, but no clue. Okay. Yeah, if you haven't taken it in a while, it's completely confusing. And to be honest with you, when I took chemistry the first time, I thought I was doing pretty well and understanding stuff, but I later realized there was a lot of stuff I just didn't get at the time and didn't get it till I took it again. So I will tell you that generally what we say is the units of the periodic table are grams per mole. Okay. And when you see it that way, then you realize exactly why you can convert to moles that way. So if I just take hydrogen to three decimal places, that'd be nice. So what I'm going to say is example, how many moles of hydrogen gas are in 14.3 grams of H2 gas. Notice I did take the time to remind you that H is a diatomic element, so you expect it to only group up in H2s. Now, I can go ahead and answer this as follows. Okay. So the molecular weight of hydrogen, or in this case, the atomic weight of hydrogen, is equal to, since I was only given three sig figs, I'm just going to write this as 1.007. I hope I don't find out that the periodic table has 1.002. I don't think it does, but if we do, we can correct it later. But I'm going to say it's 1.007 grams per mole, and that allows me, in fact, to use four sig figs, which is one more than the sig figs I have in the mass. Okay, so it's always better to use at least one extra sig fig everywhere. So that's what I'm doing here. Now, what I need to understand is the atomic weight of hydrogen is the atomic weight of hydrogen, which means hydrogen as single individual atoms floating around, which only naturally occurs in space. It's usually not in the form of H in our atmosphere. It's normally in the form of H2, where one hydrogen atom is more comfortable bonded with another hydrogen atom than it is by itself. So from this, what we can say is that the molecular weight of hydrogen H2, in other words, molecular hydrogen, is in fact 2.014 grams per mole. And that's just because the formula is H2, so that means you got to multiply the 1.007 by 2. So, as I argued, the number of moles that's normally given the symbol lowercase n, which is going to come in handy when we do the ideal gas law. It normally is the lowercase n, and in fact, I said you can get it by dividing the mass by the molecular mass. So what I'm going to do is I'm going to take the 14.3 grams of hydrogen gas of and I'm going to divide that by the 2.014 grams per mole. And this is beautiful now because you can see exactly how the units interact. Remember, when you divide by a fraction, that's the same thing as multiplying by the reciprocal of that fraction. So dividing by grams per mole is the same thing as multiplying by moles per gram. So we end up getting 14.3. Actually, let me write it this way. 14.3 divided by 2.014, like that. That's the numerical part of division. Now the unit part of division is going to be grams, which was in the numerator, so we can write that over 1, and then that's going to be multiplied by moles per gram from the denominator. And in fact, in doing so, we're going to say 14.3. Oops. I missed several digits there. 14.3 divided by 2.014 gives me 7.100. Oops. Oops, I didn't mean to do that either. Okay. I just erased everything and then did what I could do to keep from fixing that. That was supposed to be times moles per gram, and you'd see, of course, that the gram cancels out, and we should be left with just moles. So now I'm going to say equals 7.10, and then the extra digit is a 0. Notice I only had 3 sig figs in the top, but I had 4 sig figs in the bottom, so I have to round the result to 3 sig figs. And of course, putting an underline on that second 0 shows everybody that, hey, that's not a sig fig. And in fact, the result is 7.10 moles. So it turns out that 14.3 grams of H2 gas is 7.10 moles of H2 gas. So that's our answer. Hopefully that's pretty straightforward. Of course, that also allows us to see in general how do we do it for something more complicated. So let's try another example. So this time, let's say how many moles of water, oops, I didn't like my of either, moles of water are in, let's say, 250 milliliters of water. Okay. Now, I happen to know that the density of water is 1 gram per cubic, or excuse me, yeah, 1 gram per cubic centimeter. And I also happen to know a cubic centimeter is exactly equal to a milliliter. So I'm going to make use of that, but let us begin. Solution. What I'm going to do is I'm first going to realize that the density of water is equal to 1.00 grams per cubic centimeter, which is equal to 1.00 grams per milliliter. And we know that you might recall this mnemonic that I've seen teachers use, but if you draw a heart like this and then you draw a line through it, what you have is the formula for density. See, it becomes now mass over volume. So that means the mass is actually equal to the density times the volume. And therefore, we find that the mass of 250 milliliters of water is equal to 1.00 grams per milliliter times 250 milliliters is equal to 250 grams. And I'm going to put a decimal there because I need to make sure everybody understands that zero is actually is actually a sig fig. The way you could do that without this pain in the butt little decimal is you'd call it 2.50 times 10 to the 2. But that's good enough for right now. Now I'm going to remind everybody that the molecular weight of water is, in fact, I'm going to just use, let's say, 2 sig figs here just to make it easy. What I know is the molecular weight, I'll write it up here. Molecular weight of hydrogen, as I said, is 1.007. The molecular weight of oxygen is, I think it's 15.994, something like that. So, and again, these are grams per mole, and that's grams per mole. So what I'm going to do is assume that that's equal to 1.007 grams per mole. And I'm going to assume that this one is equal to 16.0 grams per mole. So with a formula like H2O, that means the molecular weight of H2O should be 2 times the molecular weight of hydrogen plus 1 times the molecular weight of oxygen, which gives us about 18.0 grams per mole. So I'm going to write that down here as 18.0 grams per mole. So now I can say that the number of moles of water in 250 milliliters is 250.0. That's another way I can do it. I can put the decimal place and then put a zero with a line under it. That line under it says, hey, this zero is not uh, significant, so the other one must be. So I've got now grams divided by 18.0 grams per mole. And that gives me 13.9. It's actually 13.888, but I'm going to call it 13.9 moles. And that's our answer. So, in fact, in 250 milliliters, which is really about a cup of water, so that's 8 ounces that's 8 fluid ounces of water, basically. So, 8 fluid ounces actually has very close to 14 moles in it. That means it's 14 times Avogadro's number is the number of molecules in an actual cup, literally, of water. So that's kind of neat, but that's what we need to do for that. Now I can go about explaining to you exactly why, if we already know Avogadro's number, you need not know the conversion for the atomic or the unified atomic mass unit. So let me explain that to you. So 1U was defined such that carbon 12, also called C12, like that. Now, what that means is that is the version of carbon that has a total number of 12 nucleons in it. Okay, the nucleons are the neutrons and the protons, and we know, for instance, that carbon has an atomic number of six, so it has six protons, and really the number of protons is what dictates what element is. So, if you have six protons, no matter how many neutrons you have, at least in terms of chemical reactions, the carbon with six protons, no matter how many neutrons it has, is always going to behave like carbon. In this case, since the nucleons is 12, that means you've got six protons and six neutrons. So 1U was defined such that carbon 12 has a mass of 12.00, infinite number of decimal places, U. Okay, so that's kind of a big deal. That's exactly how they made it, and it's kind of interesting, right? So you've got a definition now of what a atomic, or excuse me, what a carbon atom weighs, specifically a carbon 12 atom. So I should say such that the carbon 12 atom has a mass of 12U. Now, what that means is carbon, which is made up of 12 protons and neutrons total. That means six protons, six neutrons. Now, a proton and a neutron don't exactly weigh the same. They're pretty close, but not exactly the same. But the big thing is they weigh about 1,000 times more than the electron does. So, at least as a first order approximation, you can sort of ignore the mass of the electrons and just talk about protons and neutrons. So the 12 protons and neutrons are very close to weighing approximately 12U. It's actually going to be a little bit less because there's 12 electrons that weigh on the order of 1,000th of a U. Okay. Now, if you think about that, and you realize that, for instance, hydrogen has a mass of 1.007 grams per mole, then you might start thinking, well, maybe there's a relationship between them. And in fact, there is. So the fact that carbon 12, which weighs exactly 12, is 12U, can tell us something about hydrogen. Now, the key to understanding this is realizing that if you look at the periodic table and you take that mass, for instance, H being 1.007 294 or whatever. So let's say if the molecular weight of hydrogen is equal to 1.007294 grams per mole, what that means, if this weighs as much, then 1.007294 grams per mole is equal to the percent of hydrogen 1 existing in nature times the mass of H1 plus the percent of H2 times the mass of H2 plus the percent of H3 times the mass of H3 plus dot dot dot. In other words, we're going to take the percent and represent it as a decimal, and we're going to do that for the isotope hydrogen 1, which is normal hydrogen, and we multiply that, for instance, times the mass M1, MH1. So in this case, you might argue that it seems reasonable. This would be 0.9997, say. I'm just making these numbers up. It's not really true, but we're going to say something like that. Uh, Times 1.000 U plus, in this case, we're going to say 0.0003. No, let's say 5 times 1.008. something like that, U, or actually I shouldn't say U, this should actually be grams per mole, and this one should actually be grams per mole as well. Plus, again, the last result, and then any other isotopes that exist as well. Okay, all that will work out and come out to be 1.0074294. And that's where that number comes from because it's what we call a weighted average. Now, when you're done with all that, you have to divide it by the sum of all the percentages. So you have to divide it by 0.9997 plus 0.0005 plus 0.0 dot 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 plus dot dot dot. All that's how you actually compute the weighted average, and that's what's reported in the periodic table. It's the weighted average for all the known isotopes that we find. So that's why that number is not exactly one. But if you think about it in terms of carbon, it should make some sense that carbon 12 has 12 electrons, 6 protons, and 6 neutrons, and we are going to say that one carbon 12 atoms weighs 1.000 U. Therefore, Avogadro's number of carbon 12 atoms should weigh, oops, I don't know why I came out of there. 6.022 times 10 to the 23rd uh, reciprocal moles times 12.00, or excuse me, that was supposed to be a 12. I don't know why I wrote a 1 there. Hopefully you caught me on that. Okay, so since one atom's going to weigh 12, then Avogadro's number of atoms is going to weigh 12 times Avogadro's number. And according to the periodic table, we know that this is very close to 12 grams per mole. Okay. So if you look at hydrogen, specifically H1, you know that that should weigh about 1.00 grams per mole. And that in some sense, well, I'll write it this way. In some sense, a single atom should have a mass about 1.00 U, then you can see that one mole of H1 should weigh about Avogadro's number times the mass of H1 atom. Therefore, we get 6.022 times 10 to the 23rd reciprocal mole times 1.00 U turns out to be 1.00 grams per mole. So that means the individual atom, which weighs 1 U, should in fact be 1 divided by Avogadro's number. And if you take Avogadro's number and do 1 divided by it, you say 1 divided by 6.022 times 10 to the 23rd, ignoring the units for a second, what you will get is 1 divided by 6.022 times 10 to the 23rd, and that gives me 1.660577 times 10 to the negative 24. Now remember, this is all based on grams per mole, so we would expect this division coming out to be in grams. So I'll put a gram there, and therefore we see that 1U should be 1.6605 times 10 to the negative 27 kilograms, because in order to convert that grams to kilograms, you got to divide by 1,000. Now notice I only used 4 sig figs in uh, Avogadro's number, so only one, two, three, four, only four of those digits are valid. That's why this one's saying I should round that to a six instead of a five isn't necessarily valid. I just know that if I carried out the right number of digits, I'd still get that. So we now have a reason for understanding that 1U is 1 over Avogadro's number. And if you look at Giancoli's explanation of what Avogadro's number is to date, you'll see that it has a lot more decimals than just the three that I gave you. It has something quite a bit longer than 6.022. So you can look at that in what's called the front cover of Giancoli's book in my helpful documents and links module. So now we know exactly what this new unit of U is. It's 1 over Avogadro's number, and we can use that over and over. In fact, you can even use that to estimate how big atoms are or how far apart atoms are, which is what the first example in this chapter 17 does. I will cover this in our next meeting. We only have about 3 minutes left in this meeting, so I don't really have enough time to do the example that I was talking about, but I've done enough in explaining stuff. The rest of this material from the lecture should be pretty straightforward. I hope you all can follow that. And like I said, I will continue on it on Thursday with another lecture, or you can just go ahead and look for a lecture from the first days of any Physics 242 class that I've had in the past on my YouTube channel. So you can just down, not at the top, but down and right below my picture for the Physics Solutions YouTube channel, there's a little search bar down there. Type in PHY 242 and it'll bring up all the 242 ones. And if you look for 242 and then _01, you'll look for all that'll give you all the lectures that happened in January. Which obviously, if we're starting a PHY 242 course in the spring semester, the first lectures would occur in January. So that should bring up a whole several number of years of my introductory chapter 17 coverings. So check that out. Do you have any questions, Matthew? I want to remind everybody too that this is an office hour. So if you logged in as early as 6:35, I would see you before the class is over, and then I could ask you questions. So that would be the time to ask questions, and I can usually stay at least for a few minutes, but sometimes I can stay a whole hour. It says that Matthew has no questions, but maybe a minute to stay behind after the recording to ask about the course in general. That sounds fine. In fact, you can do that on the recording or not. If it's something personal or something you don't want any information about, then I can just stop recording at any point. So I'm going to stop sharing the screen right now. And I'm going to say class is now over. So fire away with any questions you have. If you are talking about something personal that you don't want on the internet, just let me know and I'll go ahead and stop the recording. But usually when students ask questions, the question is something that many students had, so the answer might be good for any student that watches this. So, any questions?
Yeah, Professor, I won't be shy. Just trying to get a handle on the format for the course in general.
Okay,
I have to confess I was a little surprised. I just logged into my computer before dinner and saw that you were holding this, so I jumped in and apologized for being a little bit late. So there is you said that this is like an office hour, or is this a you said like an actual lecture?
gotcha. Yeah, I'm treating this. So our course, if you notice, it says TBA. That's because it's what we call an asynchronous online class, which means there's not a set time where everybody is supposed to attend. In fact, people don't have to attend at all. So you attending is great if you can do it, but if it doesn't fit in your schedule, that's okay. If just the end part fits in your schedule, then show up for just the end part, and you never have to apologize for being late because you weren't necessarily required to be here. But what I do is since I'm here, Tuesday and Thursday for this particular class, I should finish by 6:40. So I ask students to come in by 6:35. And if they're here, then I can take office hours thereafter for your class as well as for any other class.
Okay, sounds good. And with the labs are obviously in person each week, correct? At the
Yes.
school. Okay. And is there one this week?
Yes, they're
Okay.
doing Intro to Excel, which is actually a pretty easy lab. So if you happen to miss it already, it's not that big of a deal to try to make up, and your teacher might even let you make it up. But I don't know, what
Okay.
day do you meet for your lab?
Well, I actually have to run to the lab in a couple minutes now. It's
Okay,
tonight, the Tuesday.
gotcha,
So I'm going to run, and my that segues to my other question. I have somewhat of an erratic schedule with home life and work. Is there
gotcha.
or are there opportunities to make up labs if I can't
Generally,
in the
no.
event
It's
they?
almost never that we can do that, especially with other instructors. Some of us, the people that aren't are not adjuncts, we actually have a repertoire of various things we can do, but the adjuncts might not have access to such things. So sometimes we can allow you to make up one, but in general, if you have an adjunct like Miss Raskovic, then she often can't do it just because she doesn't have the means to do it.
Okay. And would that include joining a different sections lab during the week?
If you can set it up, then doing another sections lab is helpful, and we normally do that in advance. So if you can set that up, by all means, clear it with your teacher and the other teacher, and we work with you as much as you can. And I can't imagine any of our adjuncts wouldn't do the same thing. They have a history
Okay.
of doing the same thing.
Okay, that's great
All right,
news. And then finally, yeah, I was the one that reached out to you about the course content, the Pearson content.
gotcha.
So I guess when that's all sorted out, we'll get
Yeah,
going on
I've
the
been talking
materials.
to Pearson all day. I don't know what's going on. They've got a lot of problems with their system. Like I just tried to reset the homeworks on the courses that did work, and just resetting the dates, it kept crashing. So something's going
Okay.
on with Pearson. Hopefully that'll be recognized and fixed within a day. But I'll give you extensions. So if you don't have enough time to complete the first homework assignment, don't worry about it. I'll give you ample time.
Okay, great.
Okay.
All right,
And there
Professor.
are
Thanks a lot.
computers on the campuses, so you could do this there instead of having to rush to a campus.
Oh yeah,
Okay.
right. Yeah, sounds good. Thanks a
All
lot.
right.
All right,
See you, Matthew.
see you next time. Yeah.
See you, little buddy. You have a good one.
If see,
Wait,
thanks.
no, say hi to our dog.
All right, buddy.
I don't mind kids. I love it. Have a good day, sir.